So what I'd like to do now is to turn things over to Pat. We're going to change gears a little bit and now hear from some of the sites, the NNCI sites, what some of the Nano IoT related things that are going on at some of the various sites. So Pat is going to MC this part of the program, and I'll turn it over to him.
Thank you, Mark. Okay. Hi, everyone. So our next speaker is Chris Ober, who is the Francis Norwood Bard Professor of Materials Engineering at Cornell University. And he is the director of the Cornell Nanoscale Science and Technology Facility, or the CNF, which is our fellow organization, NNCI organization, NNCI site. So he received his PhD in Polymer Science and Engineering from UMass. And among the things he's done, I know he was the once the chair of the Cornell Material Science and Engineering Department. And so Chris, can you share your screen and we'll get started?
I believe I can. Let's see.
Great.
Okay. So I'm grateful to have a chance to speak with you all. Unlike the previous speakers who actually live the Nano Internet of Things, as a facility director, I get to see what other people are doing and sort of live vicariously through the success of other people. So I just wanted to introduce our center to you and tell you about some of the activities and some of the developments in the area of new centers that have taken place. So I'm director of CNF, and in addition, Claudia Fischbach-Teschel is our associate director. She's an expert in the life sciences. Ron Olson is our director of operations. He comes to us from GE Power Electronics, and so he's an expert in fabrication methods and running a facility. And Lynn Rathbun is our laboratory manager, and he's been with CNF since its founding many, many years ago. We are a world-class open user facility with capabilities in micro and nano fabrication. As noted, we're part of NNCI. Our projects range from pure university research, and I'm going to talk about some of them, all the way to product development for startup companies and even large companies. And I'll say that the pandemic has affected usage somewhat, outreach especially, but we are as normal as we can be today, so please come and feel free to use the facility if you're so inclined. In 2017, we held a workshop thinking about the future of micro and nano fabrication. And from that, we elected to focus on these 5 areas: heterointegration, quantum information devices, 2D materials, life sciences, and 3D fabrication and characterization. Clearly, heterointegration fits very well in the Internet of Things. And with 2D materials, we also have a very broad base of working with both conventional and unconventional materials. And I think a number of the topics we've heard today fit very well in our life science activities. So this is what I want to tell you very briefly. Some of the capabilities and tools we have, some of the partnerships we formed in order to spin up capabilities faster than we could if we were doing it alone. Talk briefly about user research, some startups that have come from this research, and finally close with telling you briefly about CROPS, a new NSF-supported Science and Technology Center, which has many of the same goals and I think common philosophies to the Engineering Research Center we heard about. So within NNCI, we have a very advanced lithography suite. We have a Joule 9500 and a Joule 6300. So if you want to make really small things, we have the capabilities with our advanced e-beam tools. If you want to make things very rapidly using a commercial quality deep UV stepper, we have an in-house mask making capability and the ability then to produce a large number of what I like to call widgets. We do have other older, more classical UV steppers, again, mass fabrication capability. We have contact lithography, nano imprint capabilities, 3D, a 3D printer, and we have a broad expertise in resists and patterning. In the area of etch, if you're going to pattern something, often you want to etch it. We have, again, a broad material capability range, up to 20 etch chambers. More recently, we've acquired a plasma therm atomic layer etching system, which we find useful for some of the most advanced materials that we're putting through our facility. We have a number of sputtering and evaporation systems. An example of that is a new angstrom load lock evaporator just arrived. We're very excited about that. And we also have aluminum nitride deposition system, particularly useful if you're looking at piezoelectric systems and MEMS. And finally, we have our own graphene furnace, and I'll show you some examples where 2D materials or graphene-like systems can benefit from those capabilities. I mentioned that we have partnerships in order to have capabilities that we wouldn't be able to get on our own. And one is a partnership with the Cornell Institute of Biotechnology, biotech. They have just wonderful non-destructive 3D characterization capabilities ranging from confocal microscopes, super resolution microscopes, and even CT scanning capability. And so we act as a gateway to those tool sets. And in partnership with that, we have an expanded 3D fabrication capability in partnership with our mechanical engineering department's rapid prototyping lab. And so between those two, we're very excited about that and see that in some instances in the area of the nano Internet of Things, those types of tools could be very useful in building a device. I'm going to mention our neighbor, Binghamton University. They're just about a 45-minute drive from us. Because of their connection with IBM and IBM's packaging expertise, they have great strength in the area of flexible electronics and roll-to-roll production. And I can imagine in the Internet of Things, being able to build things on flexible substrates or manufacture something roll-to-roll could be advantageous. So I just want to point out that the Center for Advanced Microelectronics Manufacturing was founded in 2005. It does focus on roll-to-roll, and it has a number of lithographic and vacuum capabilities. And if you're interested in them, we'd be happy to introduce you to the folks who operate this capability. Let me just mention a few highlights of user research. The group of McEwen and Cohen and their students and former students have been interested for some time in taking 2D materials and using the fact that they can be made to fold in very precise ways to build micro robots. And so they are doing that. You can see in this graphic some origami, really kirigami here, where they built a whole bunch of folded structures. And they've learned how to build in actuators, bimorph type systems where they carry out electrochemistry or introduce charge, on a platinum surface, and it causes things to fold in a very specific way. You'll notice Mark Miskin is a co-author in this paper, and he's a new faculty member, or somewhat new faculty member at the University of Pennsylvania. So I'll have more to say about this kind of capability. In other user research, Al Molnar in our electrical engineering department is looking at putting tracking devices on honeybees And using a sensor that detects the position of the sun and knows the time of day to track the flight of honeybees and learn both where they move around, but also in the circumstance that honeybees may be endangered, help to understand some of the challenges that they face. This is an Internet of Things approach, but what it does is it has a data logger on the chip. It's a solar powered chip. And when the bee comes back to the hive, it passes through a detection system that offloads the information and then sends it out for where it can be analyzed. I think our speaker can recognize some of this work. This comes from his advisor's laboratory. And this is another take on measuring chemical potential in plants. This involves introducing what they call aqua dust into the plant, and then uses a handheld spectrometer to look at fluorescence response to these the types of challenges that that we heard about from Michael Santiago at Florapulse. And again, it's a different take on it, but it just shows the breadth of technologies you can use in the Internet of Things. But it also shows that there are other things you can do. And perhaps my question was inspired about thinking about this picture, because that looks a lot like a corn plant. And so this is another way you can learn information about the water situation of a more soft plant. So as we're talking about putting sensors everywhere, this made me recall the VAPOR program, which was supported by DARPA that I was part of. And in that circumstance, you can scatter sensors out in the field. You can, they can be visual sensors, cameras, they can be acoustic sensors, they can even be chemical sensors. And at some point, you want them to disappear. So as we put these sensors out, we're going to have the same kind of issue about how do we deal with large numbers of electronics out in the field. And this particular program funded by DARPA, the VAPOR program, developed structures that allowed you to simply disintegrate the sensor. So work out of Emmett Lowell's group at Cornell involves using types of polymers that are completely robust under normal circumstances, but can be triggered to disintegrate. And what these structures do is they fall apart into environmentally benign components. And you can imagine doing that with the entire set of the entire structure of the sensor. So I'd say lots of innovative ideas going on in our facility. And one of our roles as an NNCI site, as with all the sites, is to aid in economic development. And what you see here is a plot of the growth of startups that are partnered with CNF, use CNF, even make use of incubators that are co-located with CNF in order to grow their capabilities. An example, the one we like to brag about, is Pacific Biosciences. 10 years ago, that was a startup in Ithaca, New York. You can tell by the name it's not there anymore, but it's very likely if you had a PCR type test during the pandemic, it was a Pacific Biosciences machine. So we're pretty proud of that. Examples of how we interact with companies are through their being users. We have 120 different companies that work with CNF. To date, we have 15 new startups. Since CNF became a partner in NNCI, we have 2 incubators, Praxis and the McGovern Center. Praxis is more physical sciences, McGovern is more life sciences. And we've even brought industry from Europe to locate with us. I'd just like to mention a couple of these companies. One is OX. At the moment, they're building microscopic smart tags. You can see in this slide, here's a penny. Here's Abe Lincoln in that penny. This is the size of the sensor. So this is really nano Internet of Things. And so these folks are looking and thinking about using the ability to cheaply manufacture devices in large number. And in addition to these tags, they're also looking at microscopic robots. And the faculty who helped to found this company are thinking about the day when these microscopic robots are not tagging along, but are self-actuated, and perhaps have the ability to seek out diseases or even introduce treatment for those diseases. So a question based on this workshop that I have is, what happens when in a local area you have 100,000 of these things? How do you develop an Internet of Things to handle that? Another company, Giga, is focused on ultrasonic Internet of Things technology. It's working to increase the ultrasonic frequencies to the gigahertz frequencies. And it wants to build devices cheaply and at low cost. And so an example, keeping the theme that we heard about earlier, is the ability to make an ultrasonic device that can see underground, perhaps study the root structure without the need for a light or any other type of light source, just using sound itself. We do have a lot of experience working in the life sciences at Cornell. I mentioned the Cornell Institute of Biotechnology. Our associate director is also director of the Cornell Physical Sciences Oncology Center. And I'd like to close to talk about one example of where we have life sciences connecting to nanotechnology. And that is a new center in the area of digital agriculture called, of all things, CROPS, the Center for Research on Programmable Plant Systems. This involves Cornell, the Boyce Thompson Institute, the University of Arizona, and the University of Illinois. Like what we heard from Sherry Kagan, it is a convergence of different technologies and disciplines. It looks at the rules of life, and it involves the data revolution. So their concept is that by placing sensors, either autonomous robots or perhaps the types of sensors that FluoroPulse makes, we generate vast amounts of data. Using digital analysis, we can begin to understand and look for trends in that data. Hopefully new discoveries and predictions will come from that and lead to new experiments. But as the founders of this STC like to say, they're really looking at the language of plants. They want to listen to what the plants have to tell us through the sensors, but they also want to figure out how they can use return signals. So for example, if there's an infestation, perhaps you can alert plants to an infestation in advance. You can also listen to other plants saying, hey, there's a problem here. The idea of looking at the water level and water pressure might also be an opportunity to tell the plants to cut back on their needs or watch out, there's too much water. So with that, I'd like to wrap up and just say that, again, through a facility such as ours, we get to live vicariously through the work of others. But I think you'll see some of the interesting things related to the Internet of Things, in this case, the Internet of Living Things, that we are working on at CNF. Okay, so I'm happy to answer a few questions or make way for the next speaker, depending on where we are.
Chris, thank you so much. Very interesting talk. So if we're now open for questions. So if you have any, please raise your hand or send it through the Q&A. But in the meantime, maybe I could ask you, Chris, a couple questions. So one was really interesting. This concept of taking a polymer and making it biodegradable by sending it a trigger and it decomposes. What is the trigger that you would use?
The trigger is variable, and pardon me, I'm down to battery in one headphone here.
Okay.
In this particular case, it is heat, but it can also be light. The particular goals of this program, we were told, was to cause the polymer and other components to vanish upon reaching a temperature of 200 degrees within 2 minutes. And so we succeeded in doing that. You can do other things if you have more time. There can also be biology triggered the degradation of those components. So the ability is widespread. I'll point to John Rogers' group, who actually uses vanishing electronics for biomedical implants. That's another area where concepts and technology have been developed.
Thanks.
And I just see that, oh golly, from Mark, a comment on header integration. We have not seen any particular technologies. Traditionally, CNF has not been into the, what can I say, into the packaging space, but we are growing. There is a need for us to get more engaged in packaging, wire bonding, flip chip bonding. And in our particular case, but not applied to the Internet of Things, the use of light, communicating with light, or mixed types of semiconductors are areas that we're trying to grow our capability in because it's being driven by our users. So those are more general comments.
Chris, thank you so much. Fantastic.
Okay, thank you. Thanks to everybody for attending today.